Hi everyone, I'm just getting things ready so that I can record the video for you here next. Click away, there we go. So what we're taking a look at in this video is we're starting Unit 2, Chapter 3, where we're looking at quadratic functions. And we're beginning by taking a look at the quadratic function in the vertex form. Our goal is to make sure that you know what we mean when we say the vertex form, and then that you are able to pick out the important properties of the graph of the quadratic function if it's given to you in the vertex form. There are some vocabulary words to watch for: a vertex, axis of symmetry, maximum, minimum, domain, range. Those will all be words that we will use and talk about and that you need to be comfortable with as you talk about quadratic functions. Now, starting off with this very captivating image of a dolphin jumping in the water. And as he goes through the water, you can see that the path of the water around him is creating this beautiful shape that we know is the parabola. And what we've known from previous studies of the quadratic function is that if we had the right amount of information, we could actually create a mathematical expression that would describe the path of these water droplets or the path of the dolphin in the air. So the question would be, what would you need to know to be able to create this quadratic function describing the way this dolphin is jumping in the air? If you think about this for a little bit of time, hopefully you can come up with the fact that if you knew at the bare minimum, if you knew the vertex, so if you knew where the highest point was of his jump, and if you knew one other point on a grid of some kind, I could give you, or we could create, a mathematical expression that would describe the path of this dolphin. So let's go back through the process and review what we need to know about the quadratic function. So, of course, we have this shape that is very distinctive in front of us, this red, beautiful upside down U shape. We know this is a parabola, and a parabola is created by something we call the quadratic function. Now, there are some parts to this parabola that you need to know and be able to identify. So we talk about a line that goes straight down through the parabola and divides it symmetrically in two. It's called the axis of symmetry. The point that sits either at the bottom of the parabola or at the top of the parabola if it's upside down, these are called the vertex of the parabola. And when you have your vertex sitting at the bottom like this, we say that it is a minimum value. And when your vertex sits at the top of the parabola, we say that it is a maximum value. As well, when we look at the parabolas that we have in front of you, we will often talk about what the domain is. In other words, where are these functions defined along the x-axis? So you've got 4 different functions along here. And the interesting part is that if we were to follow along, let's say in this red one, it would continue to open up as it stretched up so that it would always be defined for anywhere on the x-axis. Even if the x was an 8, we could put it into here and we would get a value coming out. So we say that the domain of parabolas, in most cases, unless there's something unusual about them, that the domain is that x, and there are 2 ways. We can use set notation, where we use the curly bracket and say x such that x is an element of the real numbers. The next thing we talk about is the domain, and the domain has to do with how high does the graph go or how low does it go. So in this one, you can see that your graph doesn't go any lower than a -1. So we would say that the range is that this is the set of all y's where y is greater than or equal to -1, and y is an element of the real numbers. We can also use interval notation as well, and when we do an actual question on this one, I will point out how we do the difference between set notation and interval notation so that you can practice that a little bit. But for now, remembering that range describes where the graph is on the up and the down part of our coordinate plane. Here's an interesting graph. It's actually a parabola, but it's been chopped off. And so if we were to talk about this range, we would say that y is greater than or equal to 2. The domain, there's nothing over here. It starts here where x is a 0. So the domain is that x is greater than or equal to 0. So here are 2 shorthanded versions of what the range and the domain are. Again, we're going to talk about what the actual official language is that we use in a few minutes. Here's another one. Now we have as our range, you can see that it's coming from negative infinity, but it stops at -1. So we would say that the range is the set of all y's such that y is less than or equal to -1. And then when we talk about the domain, we would say, well, it exists everywhere where the x is less than 0. And so we would say it's a set of x's such that x is less than or equal to 0. Okay. Now let's focus for a minute or two upon the equation of this function. We know it's a parabola. We know that it has a vertex and an axis of symmetry, a domain, a range. But the question really is, how do we form this? Well, this is a very simple equation. It's y is equal to x squared. Now, what we're going to do next is take a look at what happens when we start to introduce different numbers into these equations. Now, if you don't remember these from previous units, you might want to find an app online and do some graphing calculator stuff online to play around with it. If you take the following function and then simply add a 3 on the end or subtract a 5, let's take a look at what happens. The red one is the at y is equal to x squared. And when you add a 3, it simply goes up 3 units from the vertex, up 3. Whereas the one that was x squared minus 5, you'll see that it's gone down 5 units, and then you have your parabola. So we say that this motion where you add a number onto the end like this is actually what we call its vertical translation. In other words, the graph moves up and down by whatever value of that q happens to be. Next, if I take some numbers and put them inside a bracket with the x, all squared, what happens? So if we look at this one, what we're going to see is here's our original in red. If we add 3, the graph actually moves to the left 3. If we subtract 5, then it goes to the right 5 and gives us the parabola that you see. Now, all of this helps us then, we'll write this down. When you have a number on the inside, it moves your graph left and right in the opposite direction from what you would expect. And that's why we say it moves left and right by the value of p, even though this is a negative p. The value has changed signs in order to go in the correct direction. Now, all of this gives us enough to be able to say, all right, well, if I have an equation that looks like the following, what is the vertex? Well, my graph is going to go to the right, P, and it's going to go up, Q. So I say that my vertex is P and Q. So when a quadratic function is in this format that you see in front of you, which we had with this style, we say it is the vertex form. And the reason we call it that is that it's so easy to find the vertex inside of this equation. Okay, the last thing we want to look at is what happens when the number at the very beginning of a quadratic function starts to change. What happens when it becomes a negative, or it turns into a 3, or it turns into a 1 over 3? Sorry, by the way, for the background noise. I hope you're able just to zone it out. Let's take a look. Y is equal to x squared is our red graph. No problem at all. When we put a negative in front of it, it flips the graph. It reflects, we say, in the x-axis. If we put a 3, then the graph becomes taller, faster, or skinnier, we might say. And if I put a 1 over 3, then the graph becomes a little flattened out in terms of its shape. So the instructions for this one are here. You can pause the video and just write down these instructions if you like. Just shows us that when this number is smaller than 0, it's reflection in the x-axis. When it's greater than 1, the graph is stretched upward. And when it is a fraction, like 1/2 or 1/4, it is, we say, compressed, so it's flattened. Okay, now it's time to actually do a few questions so you can see what they look like before you go into your homework. So a typical question is for me to give you a quadratic function, and you can tell it's quadratic because the x is squared, and that's what gives it away, but it's in the vertex form. So let's go through and pick out the different properties about the graph. I would pause the video at this point, use the instructions you see, and see if you can answer these questions yourself before you look at the answers. All right, so your vertex would be -1, -3. Your axis of symmetry is x equals -1. I've graphed what I've just described to you over here. And I have also, in order to draw a graph that's semi-accurate, I have figured out what the y-intercept was by putting in x as a 0. And when I did that, when x was a 0, I found that y was equal to -1. Once I knew that point, then I knew the point that was across, like the image across from the axis of symmetry. And that gives me the ability to draw a fairly accurate parabola. So the rest of the questions, I can see the vertex sits at the bottom. So it's a minimum value of -3 when the x was a -1. Domain is x such that x is an element of the real numbers, or I could write it in interval notation and say it's stretched from -infinity to +infinity. With the range, it's the set of all y's such that y is greater than or equal to -3, and it is an element of the real numbers. We show this with interval notation by using a square bracket for -3 because it's equal to that, and then it goes on infinitely in the positive direction. Okay, now that we've done one of those, you take a look at the second one. Pause the video, write the answers down, and then check them in the next slide. I'm not going to say much about it. I think that you can work your way through it, but do check the fine details. Pay attention to the detail to make sure that you have included everything in your answer. The next type of question that I can give you is one where I give you a graph and ask you to create the equation. Now, what's important for you to see in this picture is a couple of things. You want to notice where the vertex has been found and if it's gone through any specific points. So I've noted the vertex was 5 and -4, and it's gone through 2, -1, or it could also think of it as going through 8, -1. So what I've done to begin with is I take my standard form and put in the x and I put in the y. Please notice that this one has changed signs. And then because the graph passes through the point 2, -1, I can substitute a 2 in the x place, and I know that my answer is a -1. So I substitute things in and then go ahead and simplify this equation algebraically. And what I find is that the number that sits in front of this vertex form is 1/3. I can simply add that to my answer, and I'm good to go. Number 4 is a similar question. So I would encourage you to write down what you see, check it, and then take a look at the solutions. Good. Now, a couple questions for you. I would like you to think about it. Will all parabolas have x-intercepts? Well, after thinking about it, hopefully you can picture a couple of examples where they will not. If you have a parabola which is up here in the first or the second quadrant and it opens up, it will never cross the x-axis. Or if it's down here in the third and fourth and it opens down, it will never have an x-intercept. Will all parabolas have y-intercepts? The answer to that is yes, they will, because eventually the parabola opens and it gets wide enough that it crosses the y-axis. Okay, how many x-intercepts will each quadratic function have? So we're going to go through these one by one. What I like to do is draw a diagram, actually. So I look at this guy and realize, okay, my vertex is 0, -3. So it would be down here. Since it's positive, I'm opening up. Okay, I have 2 intercepts. The vertex here would be a 1 and a 0. So here I have a 1 and a 0. It's opening up and touching that 1 and 0, so it has 1 x-intercept. And lastly, it has a vertex of -2, -1, and it's opening down because of the negative, so it will not have any x-intercepts. Okay, now let's take a look at a couple of real-life examples, starting with the situation we looked at initially with the dolphin in a jump. We decided that if we knew the vertex and at least one other point, we should be able to find things, and so I used the following graph to help you. You can see your vertex is right there at 3 and 7, and that the graph goes through here at 9 and 4, it's definitely touching. So we put those numbers into our equation, and what we find is that the a value eventually is negative 1 over 12, and that my function would look like the following in vertex form. Lastly, taking a look at this very famous bridge. This is called the Lions Gate Bridge. It's found in the city of Vancouver. It's beautiful with the background of the mountains as well. But please notice you've got these towers, which in our account that we're going to look at, these towers are 111 meters tall. And then it's got this lovely parabola of the suspension cables. And what they say is that the cables are 67 meters from the top of the water. Okay, so now we're going to try to draw a picture of this, labeling the things they're telling us. We know the towers are 111 meters tall. We know that the towers are 472 meters apart. And we know that the lowest point of the cables is approximately 67 meters above the water's surface. So what I've done is drawn a picture of that. And then once I had a picture, then I decided, okay, what am I going to call the vertex? I decided to put it over here in the corner. And then I label my points, making sure that I know what they are relative to where that 0 is. So then I use my vertex and create an equation. Going through this one, I have to plot things in, and I will get that A is 0.00079. So there you have it. That's a really fast look through things. We've taken a look at the quadratic function in vertex form in terms of identifying it and graphing it. So good luck with your homework. Here it is. Make sure you give it a try and bring your questions to class next time.